A wing like this holds a whole plane up. Watch the air stream over it. That's where the force is hiding. Where lift comes from. The air splits at the nose. Over the top it crowds together and speeds up. Underneath it stays slower. Same air, two different speeds. So why does faster flow mean lower pressure? It comes down to energy. Follow one ribbon of air along the wing. Along that ribbon, the pressure plus the energy of its motion stays fixed. So if the air speeds up, the pressure has to drop to pay for it. That's Bernoulli's principle. Over the top, the air is faster, so right there, the pressure is low. There's a second way to see it, and it's the more honest one. Look at the streamlines over the top. They arc over, like a car going over the crest of a hill. To follow that curve, the air has to be pushed down, toward the wing, and the only thing that can push it is a pressure difference. Higher pressure up above, lower pressure below, which leaves the pressure lowest right at the surface. Suction, straight from the curve of the flow. And faster flow means lower pressure, so the top of the wing is suction, in blue. The bottom sits at higher pressure, in red. There's the imbalance, top to bottom. You've probably heard that the air has to meet up again at the back. It doesn't. That's a myth. The top flow is faster because the shape and the angle bend the air. That's the whole reason. Now add that pressure up over the whole surface. In blue, the suction on top tugs the wing upward. In red, the higher pressure underneath pushes it up as well. Every little arrow points the same way, up. Sum them all, and you're left with one net force pointing straight up. That is lift. Enough hand-waving. Here's the actual pressure the solver computed, all along the wing, from the leading edge to the trailing edge. Blue is the top surface, red is the bottom. The blue curve, the top of the wing, sits well below the red one, the bottom. That whole gap between them, added up over the wing, is the lift. Here's the very same thing from the other side. Look at the wake. The wing has thrown the air downward. Push air down, and the air pushes you up. Newton's third law. It's the same lift, just counted a different way. Watch what the angle does. Tip the nose up, into the wind, and the suction on top strengthens. More angle, more lift, pulling up. Bring it back down to zero, and the top and bottom nearly balance, almost no lift. Now tip it the other way, to a negative angle. The suction jumps to the underside, and the lift flips over and points down. Same physics, just upside down. That's exactly how a wing makes downforce. One question we skated past. Why is the air faster over the top in the first place? The answer is the trailing edge. It's sharp. Air can't whip around a sharp corner, so it has to leave the back of the wing smoothly, running off the point. That single requirement is called the Kutta condition. And to make the flow leave cleanly like that, the wing has to set up a gentle circulation around itself, a little extra speed over the top, a little less underneath. That circulation is the lift. Tilt it too far, and the air can't cling to the top anymore. It breaks away into a messy wake. The smooth suction is gone, and the wing loses its grip on the air. That's a stall. A real wing isn't one piece. An airliner coming in to land unfolds a main element and two flaps behind it, and they all pitch together as one big wing. Watch the slots between them. Each one feeds fast air onto the next piece and keeps the flow glued down, even at a steep angle, for a huge amount of extra lift. So, let's pull it together. The air runs faster over the top, so by Bernoulli and the curve of the flow, the pressure up there drops. Low on top, higher below. Summed over the wing, that's the lift. Read it the other way. The wing throws air down, and the air pushes back up. What starts it all is the sharp trailing edge, setting the circulation around the wing. More angle gives more lift, until it stalls, and a slotted flap buys you more. That's all for this video.